Okay, this is part 284C3M1B7C8E13C9C6D3p38d19d7b40. And it's line 22f1fa19c3m1b7c8e13c9c6d3p38d19d7b40. Phase noise infrared signals 5G Wow Seti. And there's the alien radio signal. And this is May 4th, 2013. Today's the 20th. So this is infrared phase noise signals for a UFO space communications device from a PDF file. Results continue in the WOW data. So this data is continuing from a previous PDF file. So I took this large PDF file and I divided it into several videos because, I didn't want to sit here all day reading to you for an hour, because that's literally how much data came up, and it was so interesting I decided to look at it because it's got a lot of stuff in it. I don't know what these frequency comb things are, but they've got a lot of the keywords in them that are in the data, so I pulled it and we'll just take a look at it and see what it's got to offer us. Okay, so this is mid-infrared optical frequency combs, and also these were the lines of data it came up in. And then CW mid-infrared OPO pump laser, then high power comb line. So you can see I've made 3 videos from one PDF file. So the keyword is Fonnula particles and wavelength formulas and Compton wavelength, and then it went to Fonnula units, tile mole, and 1472, which is what I googled and got all the PDF files. So this is a quote from a blog. Okay, so mid-infrared optical frequency combs at 2.5 ohm based on crystalline microresonators, prospects for spectroscopy and phase noise characterization. So a key requirement of an optical frequency comb is low phase noise. Although parametric sidebands can already be generated in the weak anomalous dispersion region, it has been shown recently that anomalous dispersion parameter D2 on the order of the cavity decay rate K leads to intrinsically low phase noise comb operation. The underlying physical picture is that the ratio K/D2 determines the position of the primary sidebands relative to the pump, and therefore the pathways of the comb formation process. For K/D2 and then greater than 1, the primary sidebands are far away from the pump, and spectrally separated subcombs form before merging, which results in multiple lines in a single optical cavity resonance. This leads to multiple beat notes, or more general phase noise, as well as amplitude noise. In contrast, due to the strong anomalous dispersion of MGF2 over the entire mid-infrared spectral range, figure 1C, and the high Q factors, a ratio of K/D2 and then the two little squiggly lines and 1 is attained in the mid-infrared. This results in primary sidebands close to the pump that intrinsically low noise operation can be expected as opposed to the telecom wavelength band, where high phase noise in the form of broad and multiple beat notes is frequently observed in crystalline silicon nitride infused quartz resonators and in toroids generating broadband spectra. So right there we have the word crystalline, we have silicon. Those are huge words that are in the WOW data. You have talk about quartz resonators and toroids. All those are in spectra. Those all come up for the core of the UFO spaceship, where it creates a communications device, and it also creates energy for the actual ship itself. To investigate the noise in the generated mid-infrared combs, figure 3A, one can either measure the repetition rate beat note, the heterodyne beat notes between a narrow line width CW laser and the comb lines, or the amplitude noise. On the other hand, for a high phase noise comb state, multiple or broad beat notes will be observed in the radio frequency domain along with excess low frequency amplitude noise. On the other hand, a low phase noise comb state will have a single and narrow repetition rate, or CW heterodyne beat note, and no additional amplitude noise. As ultra-fast mid-infrared detectors capable of detecting the repetition rate of tens of gigahertz frequencies are still in their development stage, and not accessible for our experiment, we investigate in this work the phase noise of the mid-infrared curved combs by first measuring the amplitude noise and second by performing a CW heterodyne beat note measurement. Figure 3b shows two comb spectra derived from a 1 mm diameter resonator with a line spacing of 70 gigahertz. This respective amplitude noise is shown in Figure 3c along with the detector background noise. No additional noise is observed, indicating that the combs have low phase noise. The experimental setup and results of the CW heterodyne beat note measurement are shown in Figure 4. Shows the optical comb spectrum investigated, which was derived from the same resonator as in Figure 3. After measuring the beat of the CW laser with the narrow line width pump, Figure 4, the beat, 4c. The beat notes between the CW laser and the different comb modes were recorded in Figure 4d. All beat notes exhibit the same line width corresponding to the employed resolution bandwidth of 300 kilowatts. Importantly, neither additional line width, broadening of the comb modes relative to the pump, nor multiple beat notes are observed in this measurement, showing that the comb lines exhibit a similar phase of phase noise at the CW pump laser. We emphasize that the phase noise in the form of multiple or broad beat notes in carrier frequency combs does not exhibit a dependence on frequency distance from the pump. So that's from www.nature.com. There's the link there. May 13th keywords, again, the mid-infrared optical frequency combs at 2.5 ohm based on crystalline microresonators. Then we're going to look at Figure 3, the phase noise investigation of the mid-infrared frequency comb modes. And this is going to continue in our next video. Thank you for watching.